Hello guys, I am happy to meet you all again in this video part 1 on waves and their applications. This is grade 11, unit 4. Guys, let's move to the lesson now. What is wave? Yes, wave is form of energy. If you take any matter, you can divide it into solid, liquid and gases. All of them have a shape and a particular arrangement of particles. But energy has no particular shape, but that is in the form of waves. So you can understand there are two major things in environment. One is matter and another one is energy. Matter is in the form of solid, liquid and gas, but energy is always found in the form of wave. So, in this lesson, we will study about waves and its type, wave motion and associated physical quantities and applications. Waves are everywhere, but what makes a wave a wave? What characteristics, properties, or behavior are shared by the phenomena that we typically characterize as being a wave? How can wave be described in a manner that allows us to understand their nature and qualities? Okay, let's move to the theory. Waves involve the transport of energy without the transport of matter. It also can be described as a disturbance that travels through a medium from one location to another location. As you all know, every matter are made up of small particles. Solids have very tight arrangement of particles. Comparatively, liquids have small spaces between their particles, but gases has very loose arrangement of particles than solid and liquids. When a wave passes through this medium, particles will not move from their rest position, but they vibrate and come back to its initial position. However, this vibration facilitates a wave to move from one point to another point. Examples: formation of ripples on a water surface and formation of waves on horizontal string. You can see some examples here. This is a string. When I vibrate that, you can see it is moving in this way. So that is the formation of wave in a string. And this is the picture which shows the waves on a sea. And in sound waves, when they produce sound, the particles in air move in this way. Each particle has collision between each other molecules. In this video, you can see the direction of wave formed when you move a rope up and down. Waves are responsible for basically every form of communication we use. Whether you are talking out loud or texting on your phone, there are going to be a wave transmitting information. So, let's learn the basics of wave and sounds in this unit. What is wave motion? If the wave transported through a medium, that is called disturbance, which travel one region to another. Disturbance means vibration of particle in the medium. Particles might be moved upward or downwards, forwards or backward, but finally it is returned to its original equilibrium or rest position. That means particles themselves do not travel along the wave. So, here you can see in this transverse wave, look at this particle, it is moving downwards, likewise, it is moving upward, and finally, it is coming to its rest position. This is wave motions. So, through this, you can understand the wave medium is not a wave and it doesn't make the wave, it merely carries or transports the wave from its source to other locations. For example, sound waves travel through air, solids, and water. So, waves can be described as a disturbance that travels through a medium, transporting energy from one location to another location without transporting matter. Formation of ripples on water. Here the medium is water. Formation of waves on horizontal string. Here the medium is a string. Okay. In addition to waves that travel through various media, there are waves traveling without a material medium. What is this? For example, we can say light waves. Although there are regions between the sun and earth without any material medium, the earth receives sunlight and heat from sun. Here, light and heat arrive at the earth as electromagnetic waves, and a material medium is not required for propagation of electromagnetic wave. Likewise, radio waves transmit from radio station to your home through air. However, as it is also an electromagnetic wave, medium is not necessary for transmission of electromagnetic wave. You can read some notes here about wave motion. Wave motion is the transfer of energy and momentum from one point of the medium to another point of the medium without actual transport of matter between two points. Wave motion always occur in one direction. This is very important. Wave motion always occur in one direction. Wave motion is classified into two different ways. They are the medium of propagation, the dimension in which a wave propagates energy, the energy transfers. The motion of the particle in each medium transmits energy in the form of wave through the medium even though the particles themselves do not travel along with the wave. Also, waves propagate through many other media. For example, sound waves propagate through air, and sounds propagate not only through air but also they travel through liquid and solids. Electromagnetic waves travel without medium, but they are also capable of traveling through the medium, but medium is not necessary for electromagnetic waves. Examples for electromagnetic waves are light waves and radio waves, and there are several other waves, infrared, ultraviolet, and there are several other waves. Okay, when you're studying about the wave, that is very important to know about the particles to particle interaction in that wave. Okay, consider the medium as a collection of interacting particles. The medium is composed of parts that are capable of interacting with each other. The interaction of one particle of the medium with the next adjacent particle allow the disturbance to travel through the medium. In the case of the slinky wave, the particles or interacting parts of the medium are the individual coils of the slinky. In the case of the sound wave in air, the particles or interacting parts of the medium are the individual molecules of air. Consider the presence of a wave in a slinky. The first coil becomes disturbed and begin to push or pull on the second coil. This push or pull on the second coil will displace the second coil from its equilibrium position. As the second coil becomes displaced, it begins to push or pull on the third coil. The push or pull on the third coil displaces it from its equilibrium position. As the third coil becomes displaced, it begins to push or pull on the fourth coil. This process continues in consecutive fashion with each individual particle acting to displace the adjacent particle. When a wave is present in a medium, the individual particles of the medium are only temporarily displaced from their rest position. There is always a force acting upon the particle that restores them to their original position. In a slinky wave, each coil of the slinky ultimately returns to its original position. As you've seen in the screen, in a water wave, each molecule oscillates and ultimately returns to its original position. It is for this reason that a wave is said to involve the movement of a disturbance without the movement of matter. The particles of the medium simply vibrate about a fixed position as the pattern of the disturbance moves from one location to another location. Waves are said to be an energy transport phenomenon. As a disturbance moves through a medium from one particle to its adjacent particle, energy is being transported from one end of the medium to the other. Think a bat is used to transport energy from the player to the softball. However, unlike wave phenomena, this phenomenon involves the transport of matter. The bat must move from its starting location to the contact location in order to transport energy. In a wave phenomenon, energy can move from one location to another, yet the particles of matter in a medium return to their fixed position. A wave transports its energy without transporting matter. Waves are seen to move through an ocean or lake, yet the water always returns to its rest position. Energy is transported through the medium, yet the water molecules are not transported. Proof of this is the fact that there is still water in the middle of the ocean. The water hasn't moved from the middle of the ocean to the shore. If we were to observe a duck at rest on the water, it would merely bob up and down in somewhat circular fashion as the disturbance moved through the water. The duck always returned to its original position, and it is not transported to the shore because of the water on which it rests is not transported to the shore. In a water wave, energy is transported without the transport of wave. Waves are categorized into two major categories: mechanical waves and electromagnetic waves. Mechanical waves require a medium for its transportation. So without a medium, it cannot be transferred from one region to another region. So there are two divisions, longitudinal waves and transverse waves under mechanical wave category. So longitudinal waves and transverse waves are categorized according to the particle motion in that waves. And next, electromagnetic waves. This is the most common medium of communication nowadays. Also, it has very high usage in technologies. And electromagnetic waves do not require a medium for its transportation. That means medium is not necessary for transportation of electromagnetic wave. With a medium and without a medium, these electromagnetic waves are capable of moving from one region to another region. Example, light, microwaves, and infrared, X-rays, and ultraviolet rays, and radio waves. Okay, let's see about mechanical waves. A mechanical wave is a wave that is not capable of transmitting its energy through a vacuum. Mechanical waves require a medium in order to transport their energy from one location to another location. A sound wave is an example of a mechanical wave. Sound waves are incapable of traveling through a vacuum. Slinky waves, water waves, stadium waves, and jump rope waves are examples of mechanical waves. Each requires some medium in order to exist. A slinky wave requires the coil of the slinky. A water wave requires water. So, mechanical waves require a medium to move from one region to another region. Here, the particle motion can be up and down or right and left and in and out around their equilibrium position. Okay, what is longitudinal wave? In the screen, you can see when we provide a pulse in left side of the slinky, the wave transport from left to right side. And this is the way of the wave direction in this slinky. So, in the longitudinal waves, the particle motion and direction of waves are parallel to each other. Direction of the wave is the direction of energy. If you take a longitudinal wave, the particles of this wave have back and forth movement. Due to this back and forth movement, longitudinal waves are characterized by rarefaction and compression. What is this? A compression is a region in a longitudinal wave where the particles are closest together. The region where the medium is compressed is known as compression. Likewise, where the medium is spread out is known as rarefaction. A sound wave traveling through air is a classic example of a longitudinal wave. As a sound wave moves from the lips of a speaker to the ear of a listener, particles of air vibrate back and forth in the same direction and the opposite direction of energy transport. In this slide, you can see the compression and rarefaction which form during the motion of longitudinal waves. Here the particle has back and forth movement. Look at this particle. It has the motion of back and forth movement. These particles vibrate in the around its rest position. They don't move from one region to another region, but from this disturbance or from this vibration, wave transport from one region to another region. Waves traveling through a solid medium can be either transverse wave or longitudinal waves. Wave traveling through a solid medium can be either transverse or longitudinal wave. Yet, waves traveling through a bulk of fluid is definitely longitudinal waves because transverse waves require a relatively rigid medium to travel in order to energy transfer. So, what do you think about waves of earthquake? Yes, seismologists have discovered these earthquakes waves are longitudinal waves because Earth's core consists of liquid most like molten ions. Okay, transverse wave. By using a slinky, we are able to produce both two longitudinal waves and transverse wave. In transverse wave, the particle displacement is perpendicular to the direction of wave propagation. That means here the particle motion is up and down, but the energy transport in the perpendicular direction. The animation shows a one-dimensional transverse plane wave propagating from left to right. The particles do not move along with the wave, they simply oscillate up and down about their individual equilibrium position as the wave passes by. Okay, you can pick a single particle and watch this motion. It has up and down motion, but particle doesn't move from its rest position, but energy is being transferred from one region to another region. Like longitudinal wave has compression and rarefaction. Crest and trough are the major characters of transverse wave. The crest is this region you can see in the upward position. A crest is a point on the wave where the displacement of the medium is at the maximum level, maximum value of upward displacement. Likewise, trough is the region of minimum displacement of the wave particle. Trough is the opposite to the crest, and this is found in the down region of the wave. Okay, now let's compare both longitudinal waves and transverse waves. Particles of medium in longitudinal wave is parallel to the propagation of the wave. Comparatively, particles of medium move perpendicular in direction to the propagation of wave in transverse wave. And Longitudinal waves consist compressions and rarefactions, but transverse waves have crest and trough. Likewise, longitudinal waves move left and right. Particles in these waves move left and right, but in transverse wave they move up and down. Likewise, longitudinal waves can propagate through solid liquids as well as in gases. But transverse wave can be propagated through solid and surface of liquid but not in gases because they need very stabilized surface to move. And what is oscillation? One wavelength is one oscillation. That means movement of particle back and forth in a regular rhythm is called oscillation. That means if you take one particle in a wave, its movement in a unit period of time, a back and forth movement in a unit time is called oscillation. And here we know time taken to one back and forth movement, that is one oscillation. Now let's move to physical quantities associated with wave motion. Waves are disturbance that spread from one point to another point. Therefore, waves have variation that depend on both time and distance. All the waves does not have same characters. They have variation between them in the frequency, in the wavelength and amplitude, etc. In the waves that we observe in nature, quite often this variation shows complex forms. However, here we are going to consider a simple form which is called sinusoidal wave. Okay, the first physical character is amplitude of a wave. Maximum displacement of particle in a wave. That means this is the rest position. From this rest position, the maximum displacement of a wave particle is in this way. This is the amplitude. This can be in meter, centimeter or millimeter units. In the sinusoidal simple waves, all the amplitudes for all the oscillations are same. And next, wavelength of a wave, that is called, the symbol is lambda, and distance between two identical points in the adjacent cycle of a wave. Wavelength is usually specified in meter, centimeter or millimeter. What is two identical points? Crest and crest, trough and trough. They are the two identical regions. So, distance between two identical regions is called wavelength. Okay, now let's compare the wavelength of two waves. If you take this wave, it has short wavelength. But here in this region, the wavelength is high. So, we can vary the waves according to their wavelength. Period. The symbol simple t. Time taken by a particle for a complete oscillation, complete wavelength. That means to oscillate, what is the time taken by that wave? So, time taken for one oscillation, time taken to make one wavelength is period. Frequency. Number of oscillation carried out by a particle in a unit time. Okay, so by dividing 1 by period, we can get the frequency of that wave. So compare these three waves. Here the wavelength is high, wavelength is low, wavelength is very low. So when the wavelength increase, the frequency will reduce. So here the frequency is low, medium frequency and high frequency. Okay, look at these waves. Here at the initial point wavelength is high, that means it has low frequency. Time to time wavelength is reducing, that means frequency is increasing. Speed. A wave travels distance equal to the wavelength in a time interval equal to the period. That means distance traveled by the waves in a unit time is speed of that wave. V equal to lambda divided by period, that means t. So, but F is already 1 divided by t. So here when we substitute this equation here, finally we get V equal to F lambda. So you have to practice some calculation in by using these formulas. Okay, let's compare both mechanical waves and electromagnetic waves. Mechanical waves require a medium for transport, but electromagnetic waves able to transport in the vacuum of empty space. Also, they are able to transport through the medium. And mechanical waves travel in the form of longitudinal wave, back and forth movement, compressional wave, and transverse wave, up and down movement. But electromagnetic waves always travel as transverse wave. All the transverse waves are not electromagnetic wave, that is just a format of a wave particles movement. And examples for the mechanical waves, sound waves, seismic waves, and rope and springs and water waves. And there are several examples for the electromagnetic waves. Let's see about these electromagnetic waves in the part 2 video of this unit. And common characteristic of these mechanical waves and electromagnetic waves are they transmit energy and but they don't transmit matter. Okay students, this is the end of the session today. Let's meet you all in video part 2 starting from electromagnetic waves with more interesting facts. If these informations were useful, click on like button. Convey your doubts and necessity through comments. Subscribe my channel for more videos. Thank you.